We're going to use Demoivres theorem and binomial expansions to enable us to take examples like this one. So example 10 we're going to use, and what we're wanting to show is that cos 6 theta is equal to something, and we're going to show it's equal to a series of powers, different powers of cos. And what we're wanting to show is this, that it's equal to 32 cos to the power of 6 theta minus 48 cos to the power of 4 theta plus 18 cos to the power of 2 theta minus 1. Now, in a typical question, you might be asked this in a number of different ways. First way is this way, which is most typical, which is to show you what the identity is and then ask you to show it, and you're going to have to go through the steps to show it. It'd be quite unusual for them to use like 6 theta, because this, as you'll see, it's quite a long process. If they're going to let you do, if they're going to give you a smaller number, they quite often may not give you the expansion that they want you to show it as. Sometimes they might just say what is, provide an expansion of cos 3 theta as a in powers of cos. Quite often they'll then ask you to do something else with this, maybe use it to show the exact value of an integral or so on, but we'll come to those type of questions later. First of all, I wanted to show you how this works, because it is quite a long algebraic slog through, and it does rely upon the binomial expansion. And the first thing I do whenever I know I'm going to have to do a binomial expansion is I write out Pascal's triangle like this. So I've got 0, 1, 2, 3, 4, 5. I've got up to the 6th power here. So I've written that out. I'm just going to put it off to one side for the moment, and we'll come back to that because we'll use it when we're putting the coefficients in. So first thing I'm going to do is use Demoivres theorem. Demoivres theorem tells us that cos theta plus I sine theta to the power of 6 is exactly equal to cos 6 theta plus I sine 6 theta. That's Demoivres theorem. Okay, so we've got this cos 6 theta here now, and what we're going to do later, once we've gone through and expanded this using the binomial theorem, binomial expansion, what we're going to do is we're going to equate the real part of this expansion with the real part over this side, because we know with an imaginary number, a complex number, the real parts equal the real parts and the imaginary parts equal the imaginary parts for two complex numbers to be the same. So let's expand this now. Cos theta plus I sine theta to the power of 6. The binomial expansion is as follows, and this is where you can make an awful mess of a question like this by basically getting the expansion wrong. So let's just do the expansion bit by bit. It's this bit to the power of 6 first. That's the first bit. And I'm going to leave the pluses and the minuses and the coefficients out for the moment. I'm going to actually let's put them all in as pluses on this first go through. Plus, then it's cos to the power of 5, and I've left a little bit of space there for the coefficient, and it's I sine theta. That's the easier one. I'm going to come back and put all the coefficients in afterwards. Then it's cos to the power of 4, and it's I sine theta squared, and I'm leaving space for the coefficient, plus cos to the power of 3 I sine theta to the power of 3, then it's plus cos to the power of 2 I sine theta to the power of 4, and it's plus cos theta I sine theta to the power of 5, then it's plus I sine theta to the power of 6. Now I'm just going to go and put the coefficients in, and it's this bottom line of coefficients, because we've got 1, 2, 3, 4, 5, 6, 7 coefficients. We've got 1, 2, 3, 4, 5, 6, 7 items here. So we can just go through and say that's a 6, that's a 15, that's a 20, that's a 15, that's a 6, and that's a 1. And that's how we put the coefficients from the binomial expansion in. Now, we have to deal with the fact that we've got i's in here, because some of them will disappear. So we've got cos to the power of 6 theta. We've got 6 cos to the power of 5 I sine theta, so nothing happens with the i's there, so we've still got 6 cos to the power of 5 I sine theta. Then we've got I squared here. I squared makes that a minus 15 cos to the power of 4 theta sine squared theta. We've now got I cubed, that's a minus 20 cos cubed I still sine theta cubed. Then we've got I to the power of 4. I to the power of 4 is a plus 1, so that stays as plus 15 cos squared sine theta to the power of 4. Then we've got I to the power of 5. I to the power of 5 is still a plus, but there's still an I left in there, so it's plus 6 cos theta I sine to the power of 5 theta. And then finally, I to the power of 6 is a minus sine to the power of 6 theta. And this we know because these are both identities, this we know must equal cos 6 theta plus I sine 6 theta. Now, this is where we say this is a complex number with a real and imaginary parts. This is a complex number with real and imaginary parts. The real parts of this side must equal the real parts of this side, and the imaginary parts of this side must equal the imaginary parts of this side. So we're only interested in the cos 6 theta, so we can cross out everything that contains an imaginary term. And we end up with cos 6 theta is equal to cos to the power of 6 theta, sorry for making a little bit of a mess there, minus 15 cos to the power of 4 sine squared theta, plus 15 cos squared sine to the power of 4 theta, minus sine to the power of 6 theta. We're getting closer, but we've got a problem here. What we're trying to get to is something that only contains cos. This contains sine. So we're going to use our old friend, the identity, and I'll show you when we get to it, minus 15 cos to the power of 4 1 minus cos squared theta, because 1 minus cos squared theta is equal to sine theta, plus 15 cos squared. Now we have 1 minus cos squared theta squared, because sine to the power of 4 is 1 minus cos squared squared. And finally, well, 1 minus cos squared theta to the power of 3. Yeah, because sine squared to the power of 3 is sine to the 6, so 1 minus cos squared to the power of 3 is the same. Now we have to do even more expansions, because if we do the first bits first, because they're quite simple, cos to the power of 6 minus 15 cos to the power of 4 plus 15 cos to the power of 6 theta. That takes care of all that bit. Then we've got to expand this bit. Okay, so we get plus 15 cos squared. Well, that's 1 minus 2 cos squared theta plus cos to the 4 theta. That's just a simple quadratic expansion. And then this is the I'll move this across so that it's a little bit clearer. Then we expand this using the binomial expansion, and we come back to our piece of paper here with our, this is what we've got when we've got a cubic 1331. So we have, and I'm going to leave the minus sign there and do this all in brackets, the first through. We have 1 minus 3 cos squared theta, because it's that cubed times that squared times that. Then it's plus 3 cos to the 4 theta, because it's that times that squared. And then finally it's minus cos to the power of 6 theta. If you're not sure what's going on there, you do need to go back and practice your binomial expansions. And finally, we're going to get rid of this brackets. We're going to expand out where we can. Cos to the power of 6 theta minus 15 cos to the power of 4 theta plus 15 cos to the power of 6 theta plus 15 cos squared theta minus 30 cos to the power of 4 theta plus 15 cos to the power of 6 theta minus 1 plus 3 cos squared theta minus 3 cos to the 4th theta plus cos to the power of 6 theta. And then finally, very finally, cos to the power of 6 theta. Well, cos to the power of 6 plus 15 cos to the power of 6 is 16, plus 15 is 31, plus another one is equal to 32 cos to the power of 6 theta, minus 15 cos to the power of 4, minus 30, that's minus 45, minus 48 cos to the power of 4 theta. Then it's looking at powers of 2, plus 15 to the power of 2, plus 3 to the power of 2 gives us out plus 18 cos to the power of 2 theta. And finally we've got our nice little minus 1 there, and there is what we were asked to show. That's a lot of work, and it's also, given that it's a lot of work, there's a lot of possibilities of going wrong. So you must set out the steps clearly. Even if you have to take this off to the side and do the expansion as a separate expansion, do that and do it clearly. It's unlikely you'd be given a cos of 6 theta. You might be given cos 4 theta or cos 3 theta to prove something like this. But you know how it's done. You can see how it's done here. If it was sine 5 theta, you do exactly the same things we've done here, but then equate the imaginary parts, and again use the identities we know in order to replace causes for sines and so on and so forth. Once we've done that, we can get down to this bit here. So there's two key things in here. One is the use of Demoivres theorem. Sorry, three key things. One is the use of Demoivres theorem. The second thing is the use of equating of coefficient of real and imaginary parts of this. And then finally there's the putting in of the identity to replace the signs to get the causes, and if it was a sign you were trying to find, it would be replacing the causes to get the signs. So there's a lot of work in there to do, a lot of things to go through, and a lot of things that can go wrong. So you do need to practice these, and you do need to go through them until you're not making simple little mistakes along the way. On pages 14 to 15, exercise 1D, question 1, A, B and C, and questions 2 and 6. Move that up a bit, don't I? So you can see it all in there. Page 14 to 15, exercise 1D, and it's questions 1A, 1B, 1C, and questions 2 and 6. Those are all of a similar type to this, and question 6 is probably is quite hard, but it does give you some hints as to the problem solving there. Give it a go, see how far you get.